Okay, hello everyone. My name is Zhao Ren. I got my PhD degree from University of Augsburg in this year, and during my PhD study, my works are mainly supported by TAPAS. So today I'd like to present part of my works for deep learning techniques for computer audition, especially on speech emotion recognition. As we know, sound is a key component of human perception of the world in our daily life. Especially, hearing is the second largest perception in the five senses of our human. To perceive audio signals, computer audition is a field of audio perceptions by machine with signal processing, machine learning, and deep learning technologies. There are several applications of computer audition, such as surveillance, health, audio-based information retrieval, and intelligent assistant. Today, we will focus on the health, and when we consider the computer audition for health, there are many applications, such as respiratory sound classification, snore sound classification, and speech emotion detection. Next, let me introduce my works according to the three main parts. The first is the generalization and protection against adversarial attacks for deep emotion recognition models based on speech. In our real world, deep learning models have been found to be vulnerable to external attacks, especially adversarial attacks. Adversarial attacks are usually well designed and human non-distinguishable. Therefore, it will lead to destructive and misinterpreted interactions. From this figure, we can see the adversarial attacks can generate adversarial data by adding the adversarial noise to raw data. Therefore, the speech emotion recognition model will give a wrong prediction to the adversarial data. In this regard, improving the robustness of deep learning models is an important factor. To analyze adversarial attacks, there are two types. One is white box adversarial attacks, and the other is black box. In white box adversarial attacks, the data and parameters are visible for the attack model. One example is fast gradient sign method. It is based on the gradient of the target model. The other is the black box adversarial attacks. Adversarial attack can be trained as CNN models in black box adversarial attacks when the attack model doesn't know the target model's data or parameters. To improve the model robustness, here in this work, we worked on the white box adversarial attacks. With adversarial training, we train the model on both real and fake data. Therefore, we will have more robust classification results. It has two advantages. The first is the training set will be larger, and the second is the parameters are regularized against more fine-grained differences. In the framework, the adversarial training contains two parts. The first part is the adversarial-based augmentation and attacks, which means we generate the adversarial data based on the raw data. The second is the adversarial-based training for defense. Here, both raw data and adversarial data are fed into the deep learning system. Therefore, the model will give a wrong prediction to the adversarial data, but give correct prediction to the raw data. But during the adversarial training, the model will be learned to predict both the raw data and adversarial data correctly. Generally, there's vanilla adversarial training. It contains two parts in the loss function. The first one is the loss function on the raw data, and it is added with the second part, the loss function on the adversarial data. However, in FGSM, the white box adversarial attacks, although the input X and the adversarial data, they are very similar. At the high level model layers, the high level representations of the raw data and fake data are quite different. Therefore, in this work, we proposed the similarity-based adversarial training. So the third part here is considered. It is calculated by the difference of the feature vectors from the raw data and feature vectors from the fake data. When these two feature vectors are regularized to be close, then the model will perform better on the adversarial data. This is our proposed methodology. To verify our adversarial training, similarity adversarial training, the three models are used: CNN4, VGG16, and ResNet50. Therefore, we can analyze the adversarial training and adversarial attacks on models with different layers. On the database of illicit mood in speech, which is an Italian speech emotion database. It has around 7 hours, and in our experiment, the data was partitioned into 3 parts: training, development, and the test. And the partitioning here is speaker independent. Therefore, our proposed model will be robust for the new coming speaker. And the data here are annotated into 7 classes. In the results, we can see that in this figure, this is the performance of the target models on the demos corpus. When the epsilon is 0, it means the model's performance on the raw data. When epsilon is larger than 0, then this is the model's performance on the adversarial data. We can see that when epsilon is becoming larger, that means the adversarial noise are morely added to the raw data. So the performance of the attack model is decreasing. This means the model can successfully attack the target model on both the development and test data. When we analyze the performance of adversarial training and vanilla adversarial training as well as single training, we can see that when we use the adversarial training, it performs better than single training on the raw data because of data augmentation for the original model with raw data only. And vanilla adversarial training is better than similarity-based adversarial training on the raw data. Finally, we can see the best performance is achieved by VGG16. But when we have a look about the adversarial data, we can see the performance are becoming worse on the adversarial data when epsilon is increasing. This is understandable because large epsilon means more difference between the real data and adversarial data. On the adversarial data, the vanilla adversarial training is worse than similarity-based adversarial training. We can see that the similarity-based adversarial training can perform better on the adversarial data, but not that good on the raw data, because the similarity-based adversarial training is based on the difference between the high-level representations of the raw and fake data. Finally, we also compare the adversarial training method with the other data augmentation methods, such as using WaveNet and noise-based augmentation. We can see that our result is better than the other data augmentation methods. The other work, apart from the adversarial attacks for deep speech-based emotion recognition models, is to enhance the transferability of adversarial attacks. In this work, we used lifelong learning. What is transferability of black box adversarial attacks? High transferability for adversarial attacks means the attacks can deceive both the already deceived target models and also a new target model. So in this way, if we increase the transferability of adversarial attacks, we can save the costs associated with learning a unified attacker and then training an independent attacker for each target model. Therefore, we can further improve the model robustness to adversarial attacks. As we can see in this figure, the high transferable black box adversarial attacks can deceive NSER models. Our framework of the proposed methodology is shown in this figure. When we give log-mile spectrograms of the speech signals to the attack model, then the attack can generate the adversarial noise. The adversarial noise is further added to the original log-mile spectrogram. Therefore, we will have the adversarial log-mile spectrogram. From these two log-mile spectrograms, we can see they are very similar. When the adversarial log-mile spectrograms are fed into the target models, all of these target models are deceived. To generate adversarial noise, we proposed a CNN model here to output a minimal adversarial perturbation. In this model, the log-mile spectrogram is the input, and then we used several convolutional layers with dilated kernels. The reason of using dilated kernels is in this way we can keep the size of the feature maps to be the same as the original input. So notably, when we generate the final perturbation, we need to regularize it to be very small. Therefore, here we used the sigmoid function here and a convolutional layer with channel number of 1 to generate the final perturbation. To train the dilated convolutional neural networks, the attack model here is optimized by such a loss function. We can see the loss function contains two parts. One is the classification loss function, and the other is the LMSE. The MSE loss function aims to regularize the difference between the original raw data and adversarial data because they have to be human indistinguishable. When we have a look at the classification loss function, it mainly aims to make the target model to wrongly predict the adversarial data. When we have the attack model and also the target model to train a highly transferable attack model, we did some analysis in this work. The highly transferable adversarial attack can deceive both already deceived target models and a new target system. So we can see that when we use single task learning, it's time consuming because we need to train adversarial attack model for multiple times for all of these different target models. Second, if we can also use multitask learning to train a common adversarial attack model to deceive multiple target models, but it requires a big memory to save all of the target models in the memory. To mitigate the big memory requirement in multitask learning, transfer learning is also possible to be used. Therefore, we can learn the adversarial attacks step by step, and at each target model can fine-tune the attack model based on the prior learned attack model, but the prior knowledge might be forgotten when we use transfer learning. Therefore, finally, we proposed to use lifelong learning. Lifelong learning aims to regularize the attack model to be able to detect both the prior learned target model and also the current target model during the fine-tuning procedure. So it has a smaller memory than multitask learning and can retain prior knowledge compared to the transfer learning. The lifelong learning method here, we used the elastic weight consolidation, EWC. From this figure, we can see when we don't use penalty, that means the transfer learning, the model will be learned to be destroyed what learned in the prior task. But when we use L2 weight, we consider all of the model parameters equally. The attack model will only remember the prior task. So in EWC, it aims to find a solution for both tasks. The idea of EWC is to give elastic constraints to the parameters of the current trained model. That means important parameters are given high constraints and unimportant parameters are given low constraints. In such a loss function of EWC, we can see that when we compute the difference between the current parameters and the prior parameters, the F, which means the feature information matrix are added here. Its diagonal can represent the importance of each parameter. It's calculated by the average on power of first-order derivatives. And lambda here is a hyperparameters. Also, this work works based on the demos database as the same as the prior work. So here, when we consider the results, we can see that when we use a bigger lambda value, that means more constraints to the parameters of the attacker and more prior knowledge is remembered. When we have a look about the order from CNN4 to ResNet 50, we can see that when lambda is larger, then the performance of the target model on CNN4 is decreasing. That means when lambda is larger, the model can remember more about the prior knowledge. This is the same when the model is attacked by the attack model with the order from ResNet 50 to CNN4. When we compare the two different target model orders from CNN4 to ResNet 50 and from ResNet 50 to CNN4, we can see that when the CNN4, which is a shallow model, the model is the attacker is more transferable on the target model than when we use ResNet 50 as the start. We also compared the model performance of single task learning, multitask learning, transfer learning, and lifelong learning on the demos corpus. We can see that lifelong learning is better than single task learning and transfer learning. The multitask learning is considered as an upper bound in the experiment. And in this work, we can also see the order of target models can affect the transferability. Shallow target model can lead to a better transferability. In summary, we mainly improved the model robustness by similarity-based adversarial training. And we also improved the transferability of black box adversarial attacks on the speech emotion recognition models using lifelong learning. And in the future, we think that in adversarial audio signal generation would be very interesting because in our works, the fake data are mainly the adversarial log-mail spectrograms. It's not audible, so adversarial audio signal generation would be very interesting, and we can listen what's the difference between the adversarial data and raw data. And furthermore, in the transferability work, we would like to verify more lifelong learning methods because EWC has its limitation that when there are more target models, it might be not able to deceive so many target models by the adversarial attacks, and more defense models will be used. This is my
Okay. I think was I the only one to have some sound problem on the very last slide? Okay.
Oh, okay.
Oh, no problem. You were
I
just,
can share it
it was the last
again.
slide and it was so strange, but it's okay.
Okay. I don't know. Okay, last slide.
No, it's okay.
This one?
You were really saying it's my last slide, and it's just at the end of this one when you were shutting down the
Ah,
presentation. So we
okay, okay.
heard everything.
Yeah.
Thank you very much. Um, are there any questions for Zhao, please? Are there? Yeah, I think it was just your laptop that, as Pascal is saying in the chat, slow down when the screen share stopped. It was strange.
Okay.
So what are the? I didn't get the motivation at first for like an attack would be to change the emotion. What kind of context are you in for the emotion-based attacks? Are there like usual cases in real life, or is it just like theoretical attacks that can be applied to anything like pathologies or speakers identification?
Yes, very good questions. Thank you, Yuli. The speech emotion recognition has been applied in many applications, such as we can consider we are using Alexa, but it can generate it should be able to recognize our emotion and give us emotional response or feedback, but it wrongly predict our emotion, then it will be a very annoying or not suitable feedback for us. I think most users won't like such application, and I think it's also related to medical applications. For example, there are several robotics and techniques were used for the autism, children's autism therapy. So one of them in autism, we need to also know these emotions of the children. So if it such application is can't is attacked, then it can't be useful to do the therapy and even harmful for the children's health, I think. Yeah, but currently all of the adversarial attacks are uh, manually, not manually, generated by human.
Mhm. Okay, thank you. Wei, do you have a question?
Yeah, thank you, Yuli. Thank you, Zhao, for your interesting presentation. Well, I'm not very familiar with adversarial attack, but I'm curious about, in general, that since you use adversarial data, which seems like it can be an option for data augmentation in speech technologies. Then I'm wondering, do you know any studies that use adversarial data in data augmentation, like for speech recognition in general, or maybe narrowed down to speech recognition for like pathological speech or children's speech or non-native speech, etc.?
Thank you, Wei. I'm thinking, in my experience, in most studies, adversarial data haven't been used for data augmentation. Yes, but in this study, we found that it can improve the model's performance. I think it should be promising to be used. Thank you.
Thank you.
Thank you very much. Pascal, you have a question?
Yeah, probably related, and also thanks for the nice and very interesting presentation and talk. And similar to Wei, we're also very interested in what you showed, that adversarial training data could be used quite nice as a supplement or maybe a replacement for augmentation. And if, for example, there are any out of the box tools or so some ways to facilitate the usage of or the generation even of these data for research endeavors in general practice basically.
Yeah, thank you, Pascal. This is a very good suggestion. I haven't seen studies working on data augmentation by adversarial attacks, but I think we can also analyze the different types of adversarial attacks and use them for data augmentation and do analysis on more data sets. Then we will know whether it's validate for data augmentation. This is only on one data set. This could be a future work, very interesting future work.
Very, very cool that you were then one of the first to pioneer this potentially. Let's see what comes out of it then. Yeah, thanks.
Thank you again for your interesting presentation. And now we will have the presentation of Enno.
Yes.
Hello, Enno.
Do you hear me?
Your audio is very low.
Should be better now.
Yeah, it's better. Thank you.
It's good enough. Okay. And can you just confirm that there's no like big black boxes covering the screen? I know there's one on the top right, probably. But
yeah,
nothing.
A little one on the top right, but it's okay.
Yeah, that's the only one. That's good. That I can't change, unfortunately. Okay.
It seems nice.
So, hi everyone. I'm Enno Hermann, and my presentation today will be part of my research on dysasphic speech recognition. I'll also cover a few aspects related to data augmentation, maybe. So maybe some of the questions from just now will be answered to some degree. So I'm a final year PhD student at EDIA and EPFL in Switzerland, working in the TAPAS project under the supervision of Matthew Megamedus. So just as a short intro, what is dysarthria? Dysarthria is a speech sound disorder, can have different causes, commonly neurodegenerative diseases like Parkinson's disease or ALS that affect motor functions, including facial muscles, which in turn will have an effect on speech. Common symptoms are imprecise articulation and slurring, because it's harder for those speakers to hit the right articulation targets. A lower speaking rate, because it takes them more time to do so, and also irregular breathing, pitch, and other symptoms. Those speakers could also especially benefit from speech technology because of general motor impairments, which makes it hard for them to complete some everyday tasks. So having kind of a smart home environment with speech control could be very useful for dysasphic speakers. Automatic speech recognition, or ASR, just at a very high level, refers to converting an audio signal, for example, me saying switch on the light, that's obtained by like a smart speaker or a phone, into the written representation. And then some other system will take that and actually try to process that and understand that that is an intention of me to actually switch on the light. And so ASR for dysaffect speech has some particular challenges, and most, or you see all currently available commercial ASR systems won't be able to handle dysaffect speech very well. So those challenges are due to, for example, the symptoms that I just described, which are lead to very large differences to typical speech. Also inter and intra-speaker variability depending on the severity of dysarthria. It can go from very mild case that is hardly noticed to more severe cases that are not understandable in general to someone not familiar with that person's speech at all. And the same speaker can also have variability due to different factors. And so if all of this leads to data scarcity, because it's hard to cover all these kind of different cases, and it's also challenging to record large amount of dysaffect speech. It's exhausting for the speakers, and it's hard to make those data sets publicly available. So there's a very limited amount of data that can be used for speech recognition training only. It's often not even designed for that purpose. What you see then very commonly in the ASR performance is large gaps between different groups of speakers. So if we look at group by severity, going from severe, moderate to mild, the differences in word error rate can be very large, regardless of the specific ASR technology used. And so for severe cases, you generally get extremely high word error rates. And see more details on that in this paper published at ICAS, for example. So those results and most of the following results and analysis as well are from the Universal Access UA speech corpus that has data from 15 dysaffect speakers and 13 control speakers without a speech disorder who are reading isolated English words. There's total about 1 to 3 hours per speaker, although there's a lot of silence in there as well. And commonly 2 blocks of words that are used for training and 1 is available for testing. So here in the paper that we published last year at Interspeech, we try to understand in a bit more detail why the performance of ASR systems varies when we train on different groups of speakers. So training, for example, on only dysaffect speech or a combination of control and dysaffect speech. And in this analysis, we found that the choice of training data has an effect on the acoustic unit space. So what are the acoustic units? So that could be phonemes, monophones, or in the context of traditional hybrid ASR systems, usually clustered context-dependent triphones, also called cenones. So generally just the classes that the acoustic model is predicting and has to distinguish between. So if we train an ASR system, we obtain a set of units, commonly by building a decision tree from the training data, clustering units. And then we can represent each unit with a Gaussian distribution that we estimate from the aligned training data. We're just using a single Gaussian here, not a GMM. And then we can compute the Kale divergence between all the acoustic units to obtain a plot like this, where darker regions indicate low Crail divergence, so higher similarity between the units. So along the main diagonal, you see units corresponding to the same phoneme, these small blobs, and then see like a large block, the vowels and the consonants in the bottom right. So these are all sorted by the phoneme class. And what we observed for systems trained on controlled speech as opposed to dysarthric speech, hope that you can see these in the plots, is that if we train on dysarthric speech, we observe much lower Crail divergence. So kind of all of the units are much more similar to each other. If we use a combination of control and dysarthric speech, it falls somewhere in the middle. Otherwise, you could take the mean or median of all the divergences. You can get some summary statistics of that as well. It's kind of including from that the choice of training data affects the acoustic unit space. So that in general is nothing that's unknown. So for example, it's generally known that dysarthria can, for example, lead to a reduction of the vowel space area. So we collect data on vowel formants and plot that. So that's from our research, control speaker and the solid lines in the outside, and then comparing with the Parkinson's disease patient on the inside, who has reduced vowel space areas, kind of the formants and vowels becoming more similar to each other. So this year is showing the same, just how that manifests in the ASR system in the acoustic model. So that comparison was kind of abstract, and next we also looked into a more concrete applicable word discrimination task, where we take pairs of words, for example, mat and bat, look at the corresponding acoustic units, or for example, M preceded by silence, followed by and so on. And then we can compare any two sequences of units using dynamic time warping, and again, using the Crail divergence between the Gaussian distributions of the units as the local distance. And if we then do these comparisons between a large set of word pairs, for example, all the words in the US speech corpus, we can compare the distributions that we get from different kinds of data. And again, we see the same pattern here, that if we have units derived from dysarthric speech, we see blue on the left here, we see on average much lower DTW distances, so it's less able to discriminate between the word pairs than for controlled speech in green here. And again, if we mix the data, it will be somewhere in the middle. And this in turn then affects the ASR performance as well. So ASR system trained on combination of dysarthric and controlled speech generally performs better than trained on dysarthric speech alone, because we see from this, because the acoustic unit space becomes more discriminable with this. So then we decided to extend this a bit, not only comparing dysarthric and controlled speech, but try to see if that holds as well for dysarthric speech of different severity. So in the US speech corpus, we have intelligibility ratings for each dysarthric speaker derived from human listeners. So here, just to see the difference, I'm just taking 3 dysarthric speakers, one with very high, low intelligibility, high severity, moderate, and high intelligibility, and you see the same pattern there as well, that the lowest intelligibility speaker has also the lowest scale divergences, where it's harder to discriminate between the words. And so this is just based on the acoustic unit space, not on the actual utterances on any audio signals corresponding to the words. So this could be done on any set of words, even if we don't have audio data for that. And here is just a plot of all the dysarthric speakers, the intelligibility ratings on the x-axis, and the median scale divergence on the y-axis from those black and white plots I showed earlier. And you see it get a reasonably good correlation of 0.81 as well. So the acoustic unit space here is a good predictor of the intelligibility of dysarthric speech. We then wanted to see if this extends to intelligibility more generally as well. So we took data from the Lizard Speech Synthesis Challenge from 2016. So it's a challenge where different groups submit samples of their text-to-speech systems, so it's unrelated to pathological speech now. And there's a shared evaluation, including evaluation of intelligibility as well, where we get word error rates from the human listeners. So here, high word error rates now correspond to low intelligibility, so it's the other way around from the previous plot. But otherwise, it's the same, plotting that against the median scale divergence. Here we see less of a correlation, as a negative correlation of 0.33. So it's there to some degree, but it's not really as clear as in the case of dysarthric speech. And this we can kind of hypothesize that it's because in the sense that dysarthric speech, there was much more homogeneous, so all the speakers had dysarthria, just of different severity, but the loss of intelligibility was kind of caused by the same patterns, and that we also know affects the articulation, whereas reduced intelligibility in the TTS systems here could be for very different reasons, because there's TTS systems based on very different technologies, and so it could be either not hitting the correct pronunciation, or there's artifacts, or general noise. So these are all very different, and so it can't necessarily be only explained by a difference in the acoustic unit space only. But at least for dysarthric speech, we found that useful. So then, as a kind of outlook from there, not really enough time to go into that in more detail, but we're now using this to examine data augmentation methods. So data augmentation generally is a method to compensate for training data scarcity, which we have here for dysarthric ASR. And there's a bunch of different methods that are being used more and more often now, specifically for dysarthric speech recognition, like just doing speed perturbation, or some more sophisticated duration modeling, because the speaking rates of the Sapphic speakers are so different. So that's something that works well. Or doing voice conversion, in particular with GANs that capture more of the speaker characteristics as well, or any other speech synthesis-based methods. So kind of the question of that is, how do we know what kinds of augmentation are actually useful? Some of them work better than others, or there are different voice conversion techniques, and it'd be nice to have a way to evaluate their suitability for speech recognition, even without training a lot of different systems. So that's where we're using this method now, so that we can try and see whether the generated kind of artificial dysarthric speech exhibits the same patterns as the actual dysarthric speech, in the sense of the changes in the acoustic unit space that I showed. So to conclude, we saw that the choice of ASR training data has an effect on the acoustic unit space. And the unit space can predict intelligibility of dysarthric speech, although not necessarily in general. And that in turn can inform about suitability of training data for dysarthric speech recognition systems. So thanks a lot for listening, and I'm happy to take any questions, or feel free to get in touch at any time.
Thank you, Enno. Are there any questions? Wei?
Yes, thank you, Yuli. Thank you, Enno, for a nice and interesting presentation. I'm wondering, because from your presentation, it seems like that the synthesis speech looks quite different from the dysarthric speech in terms of the KL divergency. And so you also mentioned that that synthesis speech may have different speech characteristics compared to dysarthric speech. But then in the Outlook, you also mentioned that, I'm not sure whether I understand correctly, but it seems like a lot of studies have used synthesis speech as a way or method of data augmentation. But then, yeah, combining these two ideas, what do you think about using synthesis to speech as a data augmentation method, and like what can we do on the synthesis speech to make it more similar to dysarthric speech, since it's much easier to collect, right, to generate than collecting the real dysarthric speech?
Yes. So yes, that's a good point. So here these results I showed are from kind of a general evaluation of speech synthesis systems that's completely unrelated to pathological speech. So they just try to develop the best TTS systems possible that sound natural, that are intelligible, etc. And so here, this measure of intelligibility was not that useful or predictive. But then to use speech synthesis or also voice conversion for data augmentation, we will need TTS systems that are specifically adapted to synthesize dysarthric speech. So here, this comparison is kind of between a lot of very different TTS systems, whereas I think that if you would take specific TTS system and see how to use it in the best possible way to generate dysarthric speech. You could train like normal speech synthesizer just on dysarthric speech, but there's other methods. There was a paper just now at ICAST that does some more clever things to be specifically suitable for TTS for dysarthric speech that is then used for data augmentation in ASR. So that's something that people do look at. I think then if you would look into that, there you should be able to see some effects on the acoustic unit space as well, because there, at least from the results you hear as well, it sounds at least similar to dysarthric speech, and it helps the ASR. So hopefully that should confirm this, but I haven't tested it yet.
Thank you. I have a following up question. Like general TTS systems are trying to generate the speech that sounds more similar to human speech, then we can think of it as a control speech to a certain extent. Then I'm wondering, like, if we replace the real human control speech by the synthesized speech, how successful it will be in a speech recognition system, for example, or like predicting the intelligibility in general.
So, I mean, just generally using TTS for speech recognition, data augmentation, without regard to pathological speech, that is something that is definitely done and that works. So, because like for language, maybe where not much data is available, but like you can train a basic TTS system, you could try and generate more data.
Do you expect the pattern will be similar to your findings, where you compare the three distributions of dysarthric plus control and control speech?
So if you then have a method of like also generating the dysarthric speech, like if you compare different things or very different systems, it will be hard to draw direct conclusions. But if you have like a comparable method to generate control and dysarthric speech, but that is otherwise the same, at least like internally, you should be able to see the differences. Yes. So like some forms of voice conversion, for example, I looked into that.
Okay. And how about if you use the dysarthric speech from human, but like the synthesis speech of control, well, the control synthesis speech, and would the pattern be similar to yours, where you have the three different distributions?
In detail, I would have to check. I mean, there's a lot of different kinds of comparisons you could do. That's kind of the challenge, and why I don't have like many more figures showing all these things, because it gets confusing quickly. But in general, yes, you should be able to see that.
Okay. Yeah. Thank you very much.
Thank you both. Thank you everyone for being here, and so we'll have another webinar next week with Viviana and Thomas. Thank you, Enno and Zhao, and have a good afternoon, everyone. Bye-bye.
Bye. Thank you.
Thank you, Yuli. Bye-bye.
Thank you.
Bye.